Hello student, welcome to EPG Pathsala. I am Anchal Srivastava from Department of Physics, Institute of Science, Banaras Hindu University. Today we are going to discuss about the module titled Basic Properties of Nanoparticles Part 7 under the paper Nanoscience and Technology 2. After completing this module, the student will be able to learn the bulk nanostructure material and their method of synthesis. You are also able to learn the failure mechanism of conventional grain size material and mechanical and electrical properties of bulk nanostructure material. Bulk nanostructure material are defined as bulk solid with a nanoscale or partially nanoscale microstructure. This category of nanostructure material has historical root going back many decades but has a relatively recent focus due to new discovery of unique properties of some nanoscale material. Early in the century, when microstructure was revealed, primarily with the optical microscope, it was recognized that refined microstructures, for example, small grain size, often provide attractive property such as increased strength and toughness in the structure material. A classic example of properties enhanced due to refined microstructure with features too small to resolve with the optical microscope was age hardening of aluminum alloys. The phenomena discovered by Alfred Wilm in 1906 was essentially explained by Merica, Walter Berg and Scott in 1999, Mehel and Kohn in 1983. And the microstructure feature responsible were first inferred by the X-ray study of Gunnier and Preston in 1938. With the advent of transmission electron microscope and sophisticated X-ray diffraction method, it is now known that fine precipitates responsible for age hardening in aluminum 4% copper alloy, for example, or cluster of copper atom, Gunnier, Preston, GP zone, and the metastable partially coherent theta precipitate by which is studied by Silcock et al. In 1953-54 and Cohen by 1992. Maximum hardness is observed with a mixture of GPI2, which is called correspondent GP zone, and theta dash with the dimension of the theta dash plates, typically about 10 nanometer in thickness by 100 nanometer in diameter. Therefore, the importance microstructural feature of age-hardened aluminum alloy in nanoscale. There are a number of other examples of nanoscale microstructure providing optimized property. The critical current density of commercial superconducting niobium-3 is controlled by grain size and is inversely proportional to grain size, with grain size of 50 to 80 nanometer providing high value of Jc. The field of nanocrystalline or nanostructure or nanophase material is a major identifiable activity in modern material science, results to a large degree from a work of 1980s by Glitter and co-workers, who synthesize ultra-fine grains material by in situ consolidation of nanoscale atomic clusters. The ultra small, less than 100 nanometer of the grain is then nanocrystallized material can result in dramatically improved or different properties from conventional grain with sizes more than 1 micrometer. Polycrystalline or single crystal material of the same chemical composition. This is the stimulus for the tremendous appeal to these materials. While there are a number of bulk properties that may be dramatically changed when the microstructure is in nanoscale, this module focuses on those for which the recent work with nanostructure material has been most extensive. There are the first, mechanical properties of nanostructure material for variety of potential structure application. Second, the ferromagnetic material with nanoscale microstructure for potential application in soft magnetic material and permanent magnet material, and for other special application such as information storage, magnetoresistance spin valve, and magnetic nanocomposite refrigerants. The solid state disordered nanostructure and their method for synthesis. As we know that the bulk nanostructures provide several improved properties such as increased strength and toughness. So, its synthesis is a very crucial and important. There are several methods for the synthesis of bulk nanostructures. Among several of them, here few are listed. The first one is compaction and consolidation. The second one is rapid solidification. The third one is gas deposition, and the fourth one is electrodeposition. These methods will be discussed one by one in the next coming slides. Let us discuss where I want to discuss the method of synthesis, which is compaction and consolidation. Compaction and consolidation is one method for the synthesis of disordered bulk nanostructures. As an example of such a process, let us consider how nanostructure copper iron alloys are made. Mixtures of iron and copper powder having the composition of your need. For example, here it is Fe85Cu15 or ball milled. Ball milled is a technique for 15 hours at room temperature. The material is then compacted using a tungsten carbide die at a pressure of 1 gigapascal for 24 hours. This compact is then subjected to hot compaction for 30 minutes at a temperature in the vicinity of 400 degrees Celsius and a pressure up to 870 megapascal. The final density of the compact is around 99% of the maximum possible density. Figure presents the distribution of grain size in the material, showing that it consists of nanoparticles ranging in size from 20 to 70 nanometer, with the largest number of particles having 40 nanometer in size. Figure shows a stress-strain curve for this case. Its Young modulus, which is the slope of the curve in the linear region, is similar to that of conventional iron. The deviation from linearity in the stress strain curve shows there is a ductile region before fracture where the material display elongation. The data shows that the fracture occurs at 2.8 gigapascal, which is about 5 times the fracture stress of iron, having larger grain size ranging from 50 to 150 micrometer. Significant modification of mechanical properties of disordered bulk materials having nano-size grain is one of the most important properties of such materials. Making materials with nano-size grain has the potential to provide significant increase in yield stress and has many useful applications such as a stronger material for automobile bodies. Let us discuss rapid solidification. Nanostructured material can be made by rapid solidification. One method illustrated in figure is called chill block melt spinning. Radio frequency heating (RF heating) coils are used to melt a metal, which is then forced through a nozzle to form a liquid stream. This stream is continuously sprayed over the surface of a rotating metal drum under an inert gas atmosphere. The process produces strips or ribbons ranging in thickness from 10 to 100 pm. The parameters that controls the nanostructure of the material are nozzle size, nozzle to drum distance, melt ejection pressure, and spin of rotation of the metal drum. The need for lightweight, high-strength material has led to the development of 85 to 94% aluminum alloys with other metals such as yttrium, nickel, iron made by this method. A melt-spun alloy of aluminum, yttrium, nickel, iron consisting of 10 to 30 nanometer aluminum particle embedded in the amorphous matrix can have a tensile strength in excess of 1.2 gigapascal. The high value is attributed to the presence of defect-free aluminum nanoparticle. Let us discuss the gas atomization and electrodeposition. In another method of making nanostructured material called gas atomization, a high-velocity inert gas beam impacts a molten metal. The apparatus is given in figure. A fine dispersion of metal droplets is formed when the metal is impacted by the gas, which transfers kinetic energy to the molten metal. This method can be used to produce large quantity of nanostructure powders, which are then subjected to hot condensation to form bulk sample. Nanostructured material can be made by electrodeposition. For example, a sheet of nanostructured copper can be fabricated by putting two electrodes in an electrolyte of copper sulfate and applying a voltage between the two electrodes. a layer of nanostructured copper will be deposited on the negative titanium electrode. A sheet of copper of millimeter thick can be made by this process, having an average grain size of 27 nanometer and enhanced yield strength of 119 megapascal. The failure mechanism of conventional grain size material. In order to understand how nano-sized grain affect the bulk structure of materials, it is necessary to discuss how conventional grain size materials fail mechanically. A brittle material fractures before it undergoes an irreversible elongation. Fracture occurs because of the existence of cracks in the material. Figure shows an example of a crack in two-dimensional lattice. A crack is essentially a region of a material where there is no bonding between adjacent atoms of the lattice. If such a material is subjected to tension, the crack interrupts the flow of stress. The stress accumulates at the bond at the end of the crack, making the stress at that bond very high, perhaps exceeding the bond strength. This results in a breaking of the bond at the end of the crack and lengthening of the crack. Then the stress building up on the next bond at the bottom of the crack and it breaks. This process of crack propagation continues until eventually the material separates at the crack. A crack provided a mechanism whereby a weak external force can break strong bonds one by one. This explains why the stresses that induce fracture are actually weaker than the bond that holds the atom of the metal together. Another kind of mechanical failure is the brittle to ductile transition, where the stress strain curve deviates from linearity as shown in figure. In this region, the material is irreversibly elongated before fracture. When the stress is removed after the brittle to ductile transition, the material does not return to its original length. The transition to ductile is a result of another kind of defect in the lattice called dislocation. Figures illustrate an edge dislocation in a two-dimensional lattice. There are also other kind of dislocation such as screw dislocation. Dislocations are essentially regions where lattice deviation from a regular structure extend over a large number of lattice spacing. Unlike cracks, the atoms in this region of the dislocation are bounded to each other, but the bonds are weaker than the normal region. In the ductile region, one part of the lattice is able to slide across the adjacent part of the lattice. This occurs between sections of the lattice located at dislocations where the bond between the atoms along the dislocation are weaker. One method of increasing the stress at which the brittle to ductile transition occurs is to impede the movement of the dislocation by introducing tiny particles of another material into the lattice. This process is used to harden steel, where particles of iron carbide are precipitated into the steel, the iron carbide particles block the movement of dislocation. Now discuss mechanical properties. The intrinsic elastic modulus of nanostructure material is essentially the same as that of the bulk material, having micrometer size grain until the grain size becomes very small, which is less than 5 nanometer. Young modulus is the factor relating stress and strain. It is the slope of the stress strain curve in the linear region. The larger the value of Young modulus, the less elastic the material. In figure, it is plot of the ratio of Young modulus E in nano-grained iron to its value in conventional grain size iron E0 as a function of grain size. We see from a figure that below 20 nanometer, Young modulus began to decrease from its value in conventional grain size material. The yield strength sigma y of a conventional grain size material is related to the grain size by a Hall-Page relation, sigma y is equal to sigma 0 k d to the power minus half, where sigma 0 is the fractional stress opposing dislocation movement, k is constant, and small d is the grain size in micrometers. Hardness can also be described by similar equation. Figure is plot the measured yield strength of iron cobalt alloy as a function of d to the power minus half, showing the linear behavior as predicted by the equation. Assuming that the equation is valid for nano-size grain, a bulk material having a 50 nanometer grain size would have a yield strength of around 4.14 gigapascal. The reason for the increase in the yield strength with the smaller grain size is that material having a smaller grain have more grain boundaries, blocking dislocation movement. Deviation from the Hall-Page behavior have been observed for the material made of particle less than 20 nanometer in size. The deviation involves no dependence on particle size, zero slope, to decrease in the yield strength with the particle size, which is negative slope. It is believed that conventional dislocation based deformation is not possible in bulk nanostructured material with size less than 30 nanometer because mobile dislocations are unlikely to occur. Examination of a small grain bulk nanomaterials by transmission electron microscopy during deformation does not show any evidence for mobile dislocations. Most bulk nanostructure materials are quite brittle and display reduced ductility under tension, typically having elongation of a few percent for grain size less than 30 nanometer. For example, conventional coarse grain annealed polycrystalline copper is very ductile, having elongation of up to 60%. Measurement in sample with grain size less than 30 nanometer yield elongation no more than 5%. Most of these measurements has been performed on consolidated particulate sample, which has large residual stress and flaws due to imperfect particle bonding, which restrict dislocation movement. However, nanostructured copper prepared by electrodeposition display almost no residual stress and has elongation up to 30% as shown in figure. These results emphasize the importance of the choice of processing procedures and the effect of flaw and microstructure on measured mechanical property. In general, the result of ductility measurements on nanostructured bulk material are mixed because of sensitivity of flaws and porosity, both of which depends on processing method. Another kind of bulk nanostructure consists of periodic layers of nanomaterial, thickness of different material such as alternating layer of TIN and NBN. These layered materials are fabricated by various vapor phase methods such as sputter deposition and chemical vapor phase deposition. They can also be made by electrochemical deposition, which is discussed in section earlier. The materials have very large interface area densities. This means that the density of atom on the planar boundary between two layers is very high. For example, a square centimeter of 1 picometer thick multi-layer film having layer of 2 nanometer thickness has been interface area of 1000 centimeters square. Since the material has a density of about 6.5 gram centimeters cube, the interface area density is 154 meter squared per gram, comparable to that of the typical heterogeneous catalyst. The interfacial regions have a strong influence on the properties of these materials. These layered materials have very high hardness, which depends on the thickness of the layer and good wear resistance. Hardness is measured using an indentation load depth sensing apparatus, which is commercially available and is called nano indenter. A pyramidal diamond indenter is pressed into a surface of the material with a load of L and the displacement of the tip is measured. Hardness is defined as LH by AH, where AH is the area of indentation. Typically, measurements are made at the constant load rate of around 20 millinewton per second. Figure shows a plot of hardness of TIN NBN nano multilayered structure as a function of bilayer period or thickness of the layers, showing that as the layer gets thinner, the nanometer range, there is a significant enhancement in the hardness until 30 nanometer, where it appears to level off and become constant. It has been found that mismatch of the crystal structure between the layered actually enhances the hardness. The compound TIN and NBN both has the same rock salt or NaCl structure with the respective lattice constant of 0.52 and 0.51 nanometer. So the mismatch between them is relatively large at hardness. Harder material have been found to have greater differences between the shear module of the layers. Interestingly, multilayer is which the alternating layers have different crystal structure were found to be even harder. In this case, dislocation move less easily between the layers and essentially become confined in the layers, resulting in the increased hardness. Let us discuss the electrical properties in this case. For a collection of nanoparticles to be conducting material, the particle must be in electrical contact. One form of bulk nanostructured material that is conducting consists of gold nanoparticles connected to each other by long molecules. This network is made by taking a gold nanoparticle in the form of aerosol, sprayed and subjecting them to fine mist of thiol such as dodecanethiol RSH, where R is C12H2 double bond. These alkyl thiol have an end group SH that can attach to a methyl CH3 and a methylene chain 8 to 12 unit long that provides steric repulsion between the chains. The chain-like molecule radiate out from the particle. The encapsulated gold particles are stable in aliphatic solvent such as hexane. However, the addition of a small amount of dithiol to the solution caused the formation of three-dimensional cluster network that precipitate out of the solid. Cluster of the particle can also be deposited on the flat surface once the colloidal solution of encapsulated nanoparticle has been formed. In plane, electronic conduction has been measured in two-dimensional array of 500 nanometer gold nanoparticle connected or linked to each other by conjugated organic molecule. A lithographic fabrication device allows electrical measurement of such an array is illustrated in figure. Figure gives a measurement of current versus voltage for a chain without line and with line A and line B linked by a conjugated molecule. Figure gives the result of the measurement of linked cluster of a number of a different temperature. The conductance G, which is defined as the ratio of current to the voltage reciprocal of the resistance R is equal to V by I is equal to 1 by G. The data in figure shows that linking the gold nanoparticle substantially increases the conductance. The temperature dependence of the low voltage conductance is given by G is equal to G naught exponential e to the power minus E by kT, where E is the activation energy. The conduction process for this system can be modeled by the hexagonal array of single crystal gold cluster linked by resistor, which are the connecting molecule as illustrated in the figure. The mechanism of the conduction in electron tunneling. The tunneling process in a quantum mechanical phenomena where an electron can pass through an energy barrier larger than that of the kinetic energy of the electron. Thus, if a sandwich is constructed consisting of two similar metals separated by a thin insulating material as shown in figure, under certain conditions, an electron can pass from one metal to another. For the electron to tunnel from one side to the other junction, there must be available unoccupied electronic state on the other side. For two identical metal at T is equal to 0 K, the Fermi energy will be at the same level and there will be no state available. In this figure, the tunneling cannot occur. The application of a voltage across the junction increases the electronic energy of one metal with respect to the other by shifting one Fermi level relative to the other. The number of electrons that can be moved across the junction from left to right in an energy interval dE is proportional to the number of occupied state on the left and the number of unoccupied state on the right, which is given by N1 E minus EV F E minus EV N2 E in bracket 1 minus F E, where N1 is the density of state in metal 1, N2 is the density of state in metal 2, Fe is the Fermi-Dirac distribution of state over energy, which is plotted in figure. The net flow of current I across the junction in the difference between the current flowing to the right and the left, which is given as I equal to K integral N1 E minus EV N2 F E minus EV minus F E D E, where K is the matrix element, which gives the probability of tunneling through the barrier. The current across the junction will depend linearly on the voltage. If the density of state is assumed constant over an energy range EV, then for small v and low t we obtained I is equal to Kn1 EF N2 EF EV, which can be rewritten in the form of I is equal to GNNV, where GNN is Kn1 EF N2 EF E Gn is defined as a conductance. The junction in effect behave as a ohmic manner, that is, with the current proportional to the voltage. So student, let us now summarize what we have learned in this module, point by point. There are several synthesis methods of disordered solid nanostructure: compaction and consolidation, rapid solidification, gas atomization, and electrodeposition. There is a failure mechanism of conventional grain size material, mainly governed by cracks and dislocation. A crack is essentially a region of the material where there will be no bonding between adjacent atoms of the lattice. Dislocation are essentially regime where lattice deviates from the regular structure, extend over a large number of lattice spacing. For a nanostructured material, yield strength increases. The reason for the increase in yield strength with smaller grain size is that material having smaller grain have more grain boundaries blocking dislocation movement. Nanostructured multilayered has layered structure, and these layered material have been high hardness, which depends on the thickness of layers and good wear resistance. The mechanism of conduction in, disordered solid nanostructures in electron tunneling. The tunneling process is a quantum mechanical phenomena where an electron can pass through an energy barrier larger than the kinetic energy of the electron. So we have learned all this in this particular module. Thank you very much.